So in the last lecture we had looked at the principles of congestion control and how TCP implements congestion control. So we looked at mechanisms like additive increase, multiplicative decrease. We saw the slow start algorithm, and we also saw how different variants of TCP, or at least I told you how different variants of TCP use information from the network to detect congestion. So the commonly used variants of TCP like TCP Reno, New Reno, TCP SAC, all of them use packet loss as a sign or indication of congestion. New variants like TCP Vegas or TCP Fast, they try to use delay as the congestion measure. So before we go on to discuss some specifics of how things are implemented in TCP, let's try and think about what are the pros and cons between using delay and loss as an indication of congestion. So suppose you had two scenarios. One scenario is you use delay as the feedback and loss as now suppose in both mechanisms you develop some sort of framework that will give you, based on this feedback, it lets you control the rate or window is controlled so that there is no congestion in the network. And both of these techniques develop mechanisms that somehow let you get to the rate exactly that will match what's available in the network. So all things being equal, that you get to the right rate, is there any benefit of using one over the other? Yeah.
The last time you mentioned delay is better for links with high bandwidth, high latency.
That's right. Delays are better for links with high bandwidth, high latency. So we'll get to exactly why that is. So that's a good answer. That's one reason why you might want to use delay. Is there any other reason why you might want to use delay or loss? Again, think of the feedback signal and what causes that feedback to arrive. Let's say the sender. Yeah.
I'm sorry? The loss, yeah, caused by bad equipment, not congestion.
That's true. But suppose it's caused by congestion.
Yeah.
I'm sorry?
If you use a packet, you don't get an extra packet, you just delay.
So you're getting to the answer. So what you're saying is if you lose a packet, then you might get into some sort of deadlock situation, right? Yeah. So the crucial part of this loss, to get this kind of a feedback signal from the network, you have to induce a loss. You have to induce some sort of bad behavior. And one problem with loss is you have to retransmit whatever you transmitted earlier. So you have wasted resources. Your packet traveled somewhere along the network and then it had to be dropped. And then it has to be retransmitted by the sender. So any loss-based mechanisms, they are inefficient in utilizing the network resources. With delay, you don't, if you get the delay information, if you get the information about the queue somehow accurately, then you're not wasting the resources. You don't need to induce a packet loss or induce retransmissions to get an idea of how much congestion is there in the network. So for that reason, if you can somehow implement this mechanism, then delay is always better than loss. Because with loss, you have to retransmit and you're wasting resources. Okay. So TCP congestion control, we already looked at what the basic mechanisms are. Roughly the rate at which TCP is going to transmit data between sender and receiver is the congestion window divided by the round trip time. So you send a window's worth of packets across to the receiver will send the acknowledgement back, and then you send another window's worth. So in every round trip time, you're transmitting the congestion window bytes across. So this is roughly the rate. And by adapting this congestion window, you can increase or decrease the rate. And that's how you control congestion in the network. And we saw different mechanisms that let you control this congestion window. So additive increase, multiplicative decrease, slow start, which is not really slow, and conservative behavior after timeout events. Remember last lecture we saw that normally you're doing additive increase, multiplicative decrease, but if you get a timeout, then your decrease is not multiplicative, but you decrease it down to a window size of 1. So timeout indicates severe congestion and you react accordingly. Now, last lecture we also argued why additive increase, multiplicative decrease is the right way to go, and not multiplicative increase and additive decrease, or multiplicative increase, multiplicative decrease. Why is that? Fairness, yeah. This mechanism ensures that in a distributed manner, the congested link divides its bandwidth equally amongst all the competing sources. So AIMD is very important for fairness. Slow start is we saw last lecture again that it exponentially increases the rate until the first loss event or until you cross a threshold. So in every round trip time, your window size is going to double. One segment, 2 segment, 4 segments, and so on and so forth, until there's a loss or until you cross some threshold. We saw this refinement. 3 duplicate acts indicate a less severe form of congestion, and that's when AIMD kicks in. The congestion window is cut in half. and then window grows linearly. And again, after timeout, the window is going to come down to 1 and they grow exponentially. So this is what the window size plot looks like as a function of time. And here time is moving in steps of round trip time. So you start with window size of 1, you increase exponentially until you reach the threshold. Then you increase linearly. The first variant of TCP, which was TCP Tahoe, did not implement the multiplicative decrease the way we understood it or the way we saw in the last lecture. What it did was, after every loss, the window size was brought down to 1, but the threshold was made half. So if the loss occurred here, the threshold becomes half, the window size goes to 1, and then you start the slow start until you reach the threshold, and then again you do additive increase, multiplicative decrease. So one refinement of TCP Tahoe was that instead of dropping the window size down to 1, when you have triple duplicate acts, you drop the window size down to half, the same as the threshold, and then continue with the additive increase. So that's the difference between Tahoe and Reno. So this is just a table defining all the actions based on the events which we already saw last lecture. So the book goes through this derivation of the TCP throughput. And then you have this formula that the average throughput by going through these steps is 0.75 times W when the loss occurs divided by the round trip time. This doesn't present the entire picture. So when you look at this formula, it's supposed to tell you how much throughput a TCP flow would receive on an average if you're connecting between two nodes which have the round trip time RTT. When you simply look at this formula, can you say what throughput your connection would receive? Is there anything missing here? Look at step 2 of this derivation. It says let W be the window size when loss occurs. How do you know what W is going to be? How can you characterize W? So if we look at so here what's said in the slide is that you're going to ignore slow start and then analyze the throughput. So if you ignore slow start, you have the window size is going to grow, then it cuts down to half, and it grows again, then it cuts down to half, grows, right? So when loss is occurring, this is your W1 when the first loss occurred, W2 when the second loss occurred, W3 when the third loss occurred. So firstly, do we have a fixed W? No. So we don't have a fixed W, but let's say what they are doing is they are trying to do an average case analysis, or they are going to look at the average throughput. So for that kind of analysis, let's assume that the losses occur periodically. So suppose you do have one constant W. And then by going through those steps, you can reach the throughput formula, which is 3 over 4 W divided by round trip time. But still, what is this W? What does it depend on? Why, under what scenario would W be, let's say, higher? And under what scenario would W be lower? How do we get to a particular value of W? Why is it not higher or lower? Or what would make W be, the average W be higher? Sorry?
The bigger and keep increasing if there's no congestion.
Well, if there is no congestion, but at some point there will be congestion. Yeah.
Share a link. Sorry? More users share a link. Sorry. If more users share a link.
More users share a link.
Then will be right, because you're sharing between more users. So what? So if more users are sharing the link, then your share is going to be lower. So this W is going to be lower. But when TCP is running, TCP really doesn't know how many other users are sharing the link, right? How is TCP receiving this information of congestion? Yeah, average throughput is going to reduce. But when I connect to any site from this computer, I don't know, my computer doesn't know how many other links are sharing the how many other flows are sharing the congested link. But somehow TCP adjusts. So what's making TCP adjust the rate? I mean, what happens here? Why does this rate go down? Because the loss is detected, right? That's when TCP is going to reduce its rate. So if your loss probability is going to be high, losses occur more frequently, then your window size is going to be low. When your loss probability is going to be low, when losses occur less frequently, then the window size will be able to grow to a much larger value. So the window size which is used here is intuitively inversely proportional to the loss probability. Do we agree on that? Right? If losses occur frequently, then this window will drop quicker. It won't be allowed to grow to a large value. So the rate at which the losses occur determines your average window size. Can we make it more explicit? We can try and derive a throughput formula for TCP based upon this loss probability and the round trip time. So if throughput is the rate at which your sender is sending data to the receiver, it's a function of the loss probability and the round trip time. So how is it related to the round trip time? The higher the round trip time, the lower the throughput. So it's also inversely related to throughput. Now let's try and derive exactly what the dependence on P is. So the way we analyzed go back and selective repeat, let's try and do the same thing. So our model is every packet goes on the network with an independent loss probability of P. So with probability P, it will be dropped. With probability 1 minus P, it will reach the receiver. Okay? So now let's try and compute this distance. Which is the number of packets which are transmitted between drops. So what is the probability that one packet is transmitted before it is dropped? One packet is transmitted before, yeah, so 1 minus P, that this is probability W is greater than 1. The number of packets, let's call this WP. The number of packets transmitted between drops. So this is probability. What is probability? WP is greater than 2. It's going to be right. The first two packets make their way, and then some other packet gets dropped. So probability WP greater than I is going to be 1 minus P right. This is similar to what we did with the analysis of go back and selective repeat. So what's the average value? This is going to be wait. The average value, if you go through the same steps, is equal to 1 over 1 minus p, sorry, which is 1 over p. Yeah. This step should have been 1 into probability WP equals 1 plus. And from this step and these identities, you can get the sum of this series to be 1 over 1 minus p, which is 1 over p. So that's saying that on an average, if your loss probability is p, you're going to transmit WP packets between losses. Right? So the lower your loss probability, the more packets you'll transmit between losses. Okay? So now let's analyze this further. So when the window, if the window is W at the time of the loss occurs, the window size goes to W over 2. Okay, so it increases from W over 2 to W periodically. So to increase from W over 2 to W, how many round trip times do you have to go through? See, this is the additive increase phase. So in every round trip time, TCP is going to increase the window size by 1. So how many round trip times? W over 2. So W over 2 RTTs. So if your, let's say, x-axis is in round trip times instead of absolute time, then this length is W over 2. Right? So x axis is the number of round trip times. So this length is W over 2. Okay? Now, in this interval, how many packets are being transmitted? In every round trip time, the number of packets that get transmitted, or the windows that get transmitted, is the current window size. Okay? So in the first round trip time, W over 2 packets will get transmitted. In the second, W over 2 plus 1, W over 2 plus 2, W over 2 plus 3, and finally W. Right? We're going to compute the total number of packets that are transmitted in this interval. So in the first round trip time, W over 2 packets go through. In the second round trip time, W over 2 plus 1 packets go through, all the way up to W. So the total number of packets that are going through is going to be the area under this curve. Right? That will give us the total number of packets that go through. So total packets So we already know that this height is W over 2. This width is W over 2. So it's this square plus this rectangle. So total packets is half W square, which is this rectangle, and then one by 2 half base into altitude of this triangle. Which is W square over 4 plus Is this part clear? Stop me if you have any doubts or any confusion.
Can you explain once more what the second term?
This second term? Well, we are computing the area under this curve to compute the total number of packets. So I have just broken that area into two pieces. One is this square, and the other is this rectangle, this triangle. So the area of the square is just square of the side. Area of the triangle is half base multiplied by the height. So that is the second term. Nothing mysterious, simply the area. Yeah. So you assume an average byte size, and now you're looking at number of packets. So window size here we are assuming to be in number of packets. You can also translate it into bytes by assuming some average packet size. So we got this figure 3W square over 8, and we had also computed this WP based on the loss probability, which was 1 over P. So we get 1 over P or W equals so your average that window size W where the loss occurs is square root 8 over 3 divided by square root of P. So the window size is inversely proportional to the square root of the loss probability. Once you have that, then your throughput formula according to the book is 3W over 4 Rtt, which becomes 3 over 4 square root 8 over 3 . Right now we have an explicit characterization of the throughput in terms of the loss probability and the round trip time. This formula is also famously known as the square root P formula. It's quite often used in practice in approximation. In this analysis, we ignored the effect of timeouts and slow start. If you include timeouts and slow start, then it becomes a little bit more complicated. But roughly, this explains the behavior of the throughput that you get versus the loss probability in the network. So the more congested your network, the higher your P is going to be, and lower would be your throughput. I'm sorry?
What do you measure?
What is the loss rate that you're getting? That gives you an indication of the congestion level in the network. So this formula has to be taken with a little bit, there are some caveats with this formula. What happens when the loss probability goes to 0 according to this formula? If the loss probability is going to 0, it indicates that there is no congestion in the network, right? So that would mean that as P goes to 0, 1 over square root P is going to go to infinity. Now would that happen in practice? Can your window size grow to infinity? No, why not? Well, suppose you have huge buffers. So in practice what happens is even if your loss probability has gone down to a very small value, your window size will grow to a certain maximum window size, and then it will remain flat. So what is happening here? Not sequence number.
No, what happens here is as flow control takes over.
Your receiver has also advertised the window, right? So the receiver, you remember when we were discussing flow control in the last lecture, the receiver had a buffer and it was advertising the free space in the buffer, and it told TCP never to send anything more than the free space here. So this is what flow control does. So this window size cannot keep on growing indiscriminately. At some point it stops when flow control takes over, and so then this sawtooth has a flat portion. So this is flow control. So the formula has some maximum which is decided by the flow control mechanism. So window size cannot go to infinity. Okay. So now we know how to plug in this value of W based on the loss probability in the network. Some constant divided by square root of P. Now look at this example. So without going through the derivation, this formula is presented, and this constant is roughly what you'll get, 1.22, some modifications. So this formula is a constant divided by round trip time divided by P, or the loss rate, times the mean segment size. So mean segment size is the average size of a packet. Remember, the formula that we derived was in terms of number of packets. So this is the throughput formula. Now consider a link which is 10 gigabits per second with the 100 millisecond round trip time. So this is a link which is high bandwidth and high delay. To achieve a throughput of 10 gigabits per second by using this formula, it requires a window size of about 84,000 or 83,300 average window size. To maintain a window size that high, your loss rate or the loss probability is going to be 2 2 into 10 to the power minus 10, which is very, 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 very small. There are a number of problems with TCP's behavior in this scenario. The first problem is this low level of loss rate, in fact, exceeds the loss rate that you might experience in the physical layers of your transmission. So your packets, they are being transmitted, let's say, on fiber. Then the bit error probability on the fiber is probably going to be higher than this. This we are assuming is the buffer overflow probability, which indicates the congestion level in the network. But if the bit error probability is going to be higher than this value, then you can never sustain a connection which will have a loss probability this low. So bit error probability would increase the loss probability and your achievable throughput goes down. That is one problem. What is the other problem with TCP? So again, let's go back to the sawtooth behavior. You have a window size here of 83,333. Your loss occurs here. What is your new window size? 40,000 or something. Now to grow back to 83,000, how many round trips time do you need? $40,000. So 40,000 round trip times of 100 milliseconds, how long would it take? Forever. Right? So what's happening is, suppose you are the only user in this link, this loss occurs here because you have exceeded the capacity of the link. Right? You overflown, some buffer has overflowed. So the rate at which you are sending here is just exceeding the capacity of the link. Then you drop down to half, and then you slowly increase. So all this available capacity you're wasting. If somehow magically that you knew that this is the rate at which you have to transmit, then maybe you would reach that rate and stay at that rate just below where you would have caused the loss and not increase the rate further. But because of the way TCP behaves, you have a very high window size, even assuming that you can have error-free transmission so that you'll have that low loss rate. Recovering from that loss takes so much time that you're going to utilize your link very, very inefficiently. All this region is sort of the wasted bandwidth of the link. Yeah.
But that was because we wanted to be fair.
That's additive increase, multiplicative decrease, right? But it has this problem of inefficiency in high bandwidth, high delay links.
Why did it drop? Absolutely speaking, from 83,000 to 40,000.
It's going to W over 2, multiplicative decrease.
Yeah, but you can't just like it shows you build up and shows you that.
That was the whole point of going through the fairness analysis last lecture. That AIMD gives you a fair allocation. So a fairly active research area is developing new versions of TCP for high-speed connections. what people have tried different approaches. If you're still working with a loss-based approach, then people have tried to modify the behavior of TCP so that this 1 over square root 2 dependence goes away. And TCP is much more aggressive in with respect to loss. So suppose it was not 1 over square root 2 but 1 over p. Then to sustain a throughput of this kind, the loss needed would be 2 to the power minus 5, 10 to the power minus 5. So that kind of a loss you might be able to sustain in a rail network, but it will still have the problem of this slow recovery. So a lot of researchers have taken a different track where they realize that doing things with loss has some fundamental limitations. So they have started to look at delay-based approaches. So in delay-based approaches, I'll give you the intuition what happens. Suppose you're transmitting at a certain rate, which is less than the capacity of the link or less than the capacity of the network. Then what's going to be the state of the buffer at the router? If you are here, are you likely to encounter any queuing delay at the buffer? No, because you're transmitting at a rate much smaller than the link capacity. As you start approaching a rate which is closer to the link capacity, your buffer will now start queuing packets. Right? The queuing delay will start increasing. So the intuition behind delay-based mechanisms is first step is you keep track of Wrttp. So you're going to keep track of the round trip time, and over time the minimum of the Wrtt is equal to the propagation delay. See, you'll send a packet, you'll get the acknowledgement back, you'll send another packet, you'll get the acknowledgement back. You'll have many different samples of round trip time. And the minimum of those samples is going to be the propagation delay. Because you assume that in your minimum you encountered no queuing delay. Okay? So then Wrtt minus min over all Wrtt is roughly the queuing delay. So every time you get a new sample, you compare it to your current minimum round trip time. The higher the difference, the more is the queuing delay that you're encountering. And by using these values, you can guess what is the rate at which you must transmit so that there is no queuing delay. And you can do this rate matching. Yeah.
Are there any efficiency in that? Because TCP, you're always trying to increase the windows up.
Yeah.
So after I drop, instead of increasing the stay level before, so when you drop, you set up your threshold again on 83,000. So when you're coming back up, instead of getting all the way to 83,000, to stay constant, say around 80,000. So you're below your last drop, where you want to keep like linear.
So you want TCP to maintain some sort of history.
Yes, and then you should do, instead of always trying to increase it, if I reach this level, of your sending constantly, so I can maintain a rate and going back. So increasing once I would drop half a week.
That's a good suggestion, but it fails under one scenario. And what's the scenario? Suppose you drop at 83,000. You come down to 40K. Now, at this point, another flow has started. Okay, so this flow is going to increase its window size. And then the next drop won't occur around 80,000, but it will occur around, let's say, 50,000 or 60,000. So if you have more flows joining in, you don't really know the exact value where you're going to fill up the link. Using this approach, this round trip time is aggregating the impact of all other flows that are sharing this link. So the queuing delay is absorbing the effect of everyone else. So by keeping this history, it will work if you are the only flow in the link. Then you know exactly. But if you're not the only flow in the link, then by keeping track of the queuing delay, you get an estimate of who else is on the link. So for instance, this queuing delay lets you set some rate or indicate some congestion. In the first round, you might have experienced that queuing delay at this particular rate. When the new flow joins in, the same queuing delay might start appearing here. So very roughly, your behavior is going to be, you set the value suppose, I'm not giving you the details of the algorithm, but once you encounter that queuing delay here, suppose you set the value to be some constant. Now this flow joins in, and the queuing delay that you observe has the effect of this flow too, because both of them are sharing the link. So then you're going to drop down your rate until at a point you don't experience queuing delay higher than this. When this flow leaves, then the queuing delay that you see is going to be lower than what you saw earlier. That would let you increase. Because you need a feedback from the network, and you don't know who else is sharing the link. That's why just keeping a memory won't work in all cases. Is the idea clear? Delay modeling, you can go through these slides. It's sort of a very detailed derivation of, if you have a fixed size object to transfer, then how long would it take, depending on slow start and congestion avoidance, how many rounds would it take? And if you go through the slides, it's very easy to understand. It's just a lot of details. So your midterm is going to be on Tuesday. It's open book, open notes. You don't need to memorize anything. You have the book. So the problems would just require some thinking. I'll ask a question the way I've asked questions in the homework. Just try and think and analyze the situation. And nothing which is nothing beyond what has been covered in class is going to be asked. Roughly it translates to chapter 1 to 3 of the book. But just go through the concepts that we have gone through in class, like the concept that we went through when we discussed transport layer. Concepts of reliable data transfer, what you need to do, concepts like flow control, congestion control, multiplexing, demultiplexing. When we did the application layer, this is the notion of what are sockets, socket programming, naming, discovery. So there might be a problem where you might be asked to do some sort of simple performance modeling of this kind. Go back and a selective repeat or something similar to that. But did you have questions on the midterm? It's going to be in class, 75 minutes. Nope. Yeah.
It's not been posted.
I've given it to the TA. I'll make sure that it is posted. Yeah.
So then it's probably good.
You want to use your laptop?
For what? Googling answers? I mean, you can bring your laptop. I'm cooking up most of the problems myself, so I don't think you'll find answers there, but you won't need it. Just bring the textbook along, class notes, that should be fine. So I'm traveling on Tuesday, so I'm not going to be here doing the exam, but the TAs would be here, and there shouldn't be any major questions, but if there are, the TAs would have my cell phone number. They can call me. Okay, good luck for the midterm.
Still have class